If you live in a warm climate, you probably do not pay too much attention to the safety features of your vehicle, since roads in warm climates seldom subject you to hazardous conditions. However, if you live in a winter climate, when there is a much higher likelihood of hazardous driving conditions, especially in winter with snow and ice, then you probably have a much greater appreciation of your vehicle's safety features. The two safety features that we'll discuss in this video are the Antilock Brake System, known as ABS, and the Electronic Stability Control System, which is known as ESC. Both of these systems work together and also in a similar fashion in order to prevent the loss of vehicle control and to still maintain steering ability during hazardous road conditions. ABS works by detecting when a wheel locks and stops spinning while the vehicle still has forwards velocity. Sensors in the vehicle determine its forwards momentum and acceleration, and sensors within the wheel itself determine the wheel's rotational speed. During a sudden stop event, when the brakes are suddenly fully engaged, the wheel's rotational speed will reach zero because of the strong brake force application, most likely before the vehicle's forward velocity reaches zero. This, of course, is dependent upon speed. If the vehicle is traveling at a high speed, or if the road is just too slippery, then the wheels themselves will reach 0 RPM, significantly before the vehicle's forwards velocity and momentum have a chance to reach zero. This, of course, will result in the wheels being locked against the brake calipers, so the wheels are at 0 RPM, while the vehicle is still traveling forwards. So this is what will result in a skid until the vehicle comes to a stop. This is where the role of the ABS comes in, to rapidly pulse the brakes on a wheel whose RPM is rapidly approaching zero or already is zero, while the vehicle still has a significant forwards velocity and momentum. Pulsing the brakes with the ABS allows the wheel to still roll against the pavement instead of skidding while locked, which results in a much more effective stop and also allows the driver to maintain steering control of the vehicle. If you are driving on a very wet road or a road covered in snow and ice in the wintertime, there will be a lot less traction between the tires and the road, and the ABS will become much more active. This will be shown with the upcoming force balance diagram. So to start, the example that will be used in this video is a vehicle behavior when accelerating and braking on a road where the left half is covered with snow and ice and the right half is clear asphalt. So as your vehicle is driving on a road like this, first it's just asphalt without ice, but then once it approaches the section of the road where you do have ice, if the brakes are engaged while driving on this kind of a road, then the vehicle will start to torque in the clockwise direction. And this is because the snowy or icy part of the road is more slippery, requiring a greater stopping distance due to less frictional resistive force from the snow. These red arrows show the friction force, and this is what results in the clockwise torque. The vehicle will stay in this kind of swerving condition until the ABS activates and allows for the skidding wheels to begin rolling again, thus removing the force imbalance and correcting it and then stabilizing the vehicle. The driver will also be able to steer more easily. With locked and skidding wheels, the driver cannot steer. Next up, we will discuss ESC, the Electronic Stability Control. This system is used when one or more wheels start slipping on a slippery surface as the driver is accelerating. So this is when power is applied to the wheels when the driver presses the accelerator pedal. The same wheel speed sensor, which relays to the ABS module that the wheel speed is approaching zero, now sends a signal to the ESC module if a wheel speed is significantly greater than the speed of the other wheels, or than the speed at which it should be based on engine RPM and engine torque output, which is calibrated within the vehicle's powertrain control module. This situation would indicate that the wheel has lost traction with the ground and has begun to slip, thus causing the excessively high RPM. Now in this case, if the driver starts accelerating while driving over this kind of a road, the vehicle would begin to lose traction on the ice. And this can be seen here by the green force arrows. So the vehicle has traction on the asphalt, good traction, and then much less traction on the ice. And this, of course, would result in a force imbalance that would lead to a counterclockwise torque of the vehicle as it loses traction while accelerating on ice. This would continue, of course, until the ESC activates to reduce power to the slipping wheel, allowing regain of control of the vehicle. Once the driver notices the swerving of the vehicle, he or she may also try to correct it by steering the wheel but this would only be effective once the wheels stop slipping. The ESC should limit power to the non-slipping wheels as well, based on the torque limit delivered to the previously slipping wheel. To give a numerical example of ESC limiting torque to slipping wheels versus non-slipping wheels, let's look at it this way. So let's say that the ESC has limited the torque to the slipping wheels on the ice to 50 Newton meters. This means that 50 Newton meters is the maximum amount of torque that the wheel can receive just before beginning to slip. Based on this, the wheels on the asphalt side of the road, if they also receive 50 Newton meters of torque, they will automatically have more traction on the asphalt than on the ice due to the higher friction coefficient of asphalt. So, in order to completely prevent a force imbalance, those wheels on the asphalt should receive less than 50 Newton meters of torque, so maybe 40 Newton meters. This will really even out the force imbalance and eliminate it almost completely. Shown here now will be the vehicle's free body diagram as it's moving freely along the road without any acceleration or braking. The wheels on the ice side of the road will naturally have less traction since the coefficient of friction of ice and snow is much lower than that of asphalt. Even if the vehicle is just rolling forward without driver input of any kind, it could still start to swerve when it hits an icy portion of the road. This, of course, depends on speed because the wheels could start to lose grip even at moderate speeds. In this case, the ESC could even gently apply the brakes to a wheel if its RPM is too high and it's slipping, allowing it to roll slower and with more traction on the ice. If we break this down a little bit more, friction is what actually allows a rolling wheel to move forward in the same way that friction is the force that actually allows you to walk forward. When you take a step forward, your foot has forwards force as your heel strikes the ground, shown by the green arrow. The ground then exerts a frictional resistive force in the opposite direction back onto your foot, which is Newton's third law, equal and opposite reaction. This friction force is what keeps your heel in place on the ground, allowing you to then transfer your weight onto the forward foot. You begin to move forward as your back heel comes off the ground, and you drive through your back toes, shown by the green arrow pointing to the left. Your back toes then exert a backwards force on the ground, and the ground in turn exerts a friction force in the opposite direction on your toes, in the forwards direction. This is how you're able to walk forward because the friction force actually pushes your back foot forward and allows the completion of the weight transfer onto your front foot. That's why if you try to walk on ice and you take a big step forward, you have the same forwards force as you did when you were walking on a dry surface. There is very little frictional force from the ice to counter the forwards force of your front heel, causing you to slip forward. This is shown by the blue arrow, which is the frictional force from ice, significantly less than that from a dry surface. Also, with your back foot, there's not enough friction for you to counter the backwards driving force of your back toes, causing your back foot to slip backwards. If you try to walk on ice, you'll essentially cause yourself to do a split. Now, hopefully this will give you an appreciation for how friction allows you to walk, and you can understand exactly why you should never take big steps on ice, because this is exactly the situation that would happen. If we return now to the vehicle and wheel free body diagram, we can see how the same friction force that allows you to walk forward is also what allows a wheel to roll forward. To drive forward, a positive clockwise torque is exerted on the wheel during acceleration. This torque is then translated into a linear force. Force is torque times radius of the wheel, and this linear force is exerted backwards against the road. The road in turn, due to Newton's third law, exerts a forwards linear friction reaction force, pushing the wheel forward. This happens on all four of the wheels. This is what, of course, allows the wheel to roll, the friction force reacting from the road back onto the wheel and pushing the wheels forward. However, from this free body diagram, if a wheel receives a large input force, more than what the surface on which it's rolling can exert back on the wheel due to friction, this will contribute to a local force imbalance on the wheel. The wheel is slipping due to loss of traction, and this will translate into a larger force imbalance on the entire vehicle, where you have a stronger friction reaction force on the side with good traction on the asphalt, and a weak friction reaction force on the side with ice. This is what results in an overall counterclockwise vehicle torque, and subsequently resulting in a swerve of the vehicle as it rolls over ice. Next up in this diagram, we can see exactly how static friction, which is exerted on a stationary body, works on a rolling wheel versus kinetic friction later on. First of all, friction is coefficient of friction times the force on the surface, which is weight or force applied to the surface. A larger force applied to a surface or a heavier weighted object will see a higher friction force reaction. So you can think of lightly placing your hand on a table and attempting to move it forward along the table versus pushing your hand more forcefully down into the table and then attempting to move your hand. It's much harder to move your hand if you push it forcefully into the table because there's more friction force this way. The small wheel input torque results in less force into the ground from the wheel, which in turn results in less frictional force from the ground. However, a high wheel torque, of course, will have a large force into the ground, and subsequently this will result in a large friction reaction force. However, if the force of the wheel into the ground is very high, then only so much of this can be matched by the static friction. Any remaining force not matched by friction will result in the wheel slipping, since first of all, static friction will be overcome, and then second of all, the force imbalance is going to be balanced out by extra torque sent back into the wheel. This is what results in the slipping, and this is also due to conservation of energy. Even on dry asphalt, if too much acceleration is given, then the wheels will slip and you'll have what's known as a peel. So in a normal situation, static friction between the wheel and the road will be maintained as long as there's a single point of contact between the wheel and the surface. And this can be shown in this example here. So as the wheel receives input torque and exerts force against the ground will exert an equal and opposite friction reaction force. And here you can see how a tire rolls and moves forward in slow motion by maintaining a single point of contact with the ground. And in a basic dynamics class, this is how static friction and single point of contact for a rolling wheel would be shown. On the other hand, for kinetic friction, this is force exerted on a moving body, and it's always less than what static friction would be. The force against the ground from the wheel is now greater than what can be matched by static friction, so static friction is now overcome, resulting in kinetic friction, which is less. Now the wheel is slipping and skidding forward since there is no longer a single stationary point of contact with the ground. This can be shown here in this diagram. The force against the ground from the wheel is significantly greater than what the friction can match. So now the force imbalance is made up for by an excess wheel torque. The wheel is now slipping in place, and the forwards motion of the vehicle itself now causes the wheel motion to look more like this, more like a skidding motion. And this is also what would be shown in a dynamics class for a wheel skidding. Now that we know the difference in wheel rolling and movement when there's static friction versus kinetic friction, we can take a look at the vehicle's free body diagram for the case when it is accelerating. When the driver presses the accelerator pedal, power is applied to the wheels and they begin to slip on the icy part of the road while maintaining traction on the asphalt side. The rotational force of the wheel accelerating acts backwards against the road, shown by the red arrows here. The road in turn exerts a friction reaction force back on the wheel, shown by the green arrows. As mentioned previously, the icy part of the surface exerts less friction than the asphalt. The localized force imbalance at the wheel causes an over-torque, which results in the wheel slipping in place. At this point, grip with the ground is lost completely, and the friction reaction force is diminished even further, since now kinetic friction has overtaken static friction. On the asphalt side of the road, friction from the road still is able to match the force of the wheel against the road, so no slipping is happening here. The localized force imbalance at the wheel due to over-torque translates to a force imbalance on the entire vehicle, in that the larger friction reaction force on the asphalt side results in a net torque, or a net counterclockwise torque, of the vehicle as it's trying to accelerate on ice. Now, this is where the ESC system comes into play, since it reduces or in some cases entirely cuts off power to the slipping wheels, allowing for them to regain static one point of contact between the wheel and the road, regaining static friction. This will allow for two things. Number one, there will no longer be a localized force imbalance at the wheel since there is an excessive torque being applied to the wheels on ice. The amount of torque applied to the wheel and its subsequent lateral force on the road should now equal the friction force that the icy surface is able to counteract with. This is the result of the power output reduction to the slipping wheels. Now that the wheels are no longer slipping and there is traction with all four wheels, static one point of contact, the friction from the icy part of the road will be greater, hopefully matching that of the asphalt side. The vehicle's counterclockwise torque will, as a result, be reduced or eliminated completely due to a reduction or elimination of the force imbalance. However, as a quick side note, friction force of ice is still lower than that of asphalt, even when there is static friction. So the ESC would need to reduce some power to the wheels on the asphalt side as well, to make sure that their torque does not exceed that of the wheels on ice. The asphalt side wheels should probably receive less torque than the ice side ones to balance out the difference in friction forces from the two surfaces. Lastly, we will look at the free body diagram for vehicle braking, which actually is opposite of the acceleration free body diagram. The braking force or the stopping force experienced by the vehicle to slow it down actually comes from the forwards inertia and momentum of the vehicle being counteracted by friction force from the road as the brakes are applied. It can be thought of like this. When the brakes are applied, the vehicle loses velocity, but its inertia and momentum want to keep it going forward. Inertia is defined as the desire for an object in motion, or at rest, to stay in motion, or stay at rest. Any change in object velocity or direction will be met by a resistance force of some kind in order to preserve conservation of energy. If an object is moving forward and is suddenly stopped, it will experience a continuing forwards force to keep it moving forward. In the case of the vehicle's forwards momentum will be met by resistance, which is friction, from the road as the brakes are applied. On an icy surface with friction force being reduced, the stopping distance for the same forwards force will be greater than on the asphalt. This once again results in a force imbalance, this time with braking force to stop the vehicle being greater on the asphalt and reduced on the ice, causing the vehicle to again torque clockwise. Additionally, this force imbalance is exacerbated due to wheel locking on a slippery surface. If the vehicle is coming to a rapid stop from a high speed, the brakes are engaged forcefully, almost fully, in an attempt to bring the vehicle speed to zero as quickly as possible. If the brakes are fully engaged, the wheel speed could come to zero before the vehicle speed does so if the vehicle is traveling fast enough. If the vehicle speed still hasn't gotten a chance to come to zero, then the locked wheels will skid along the surface until the vehicle can eventually come to a stop. This once again is now kinetic friction and no longer static friction, increasing stopping distance even more. Of course, the wheels will lock and start skidding much faster on ice than on asphalt because of less frictional force from the ice. So the wheel speed will reach 0 RPM on ice long before the vehicle speed has a chance to slow down to zero. To compare with dry asphalt at moderate speeds, with a fully engaged brake, the wheel speed will reach zero around the same time as the vehicle speed reaches zero. So no skidding should ever happen on asphalt unless you're traveling at excessively high speeds and you forcefully engage the brake. Now if we look at the free body diagram, we can see the green arrows as the force of the vehicle moving forward. And then we can see our braking force here, the kinetic friction slowing the vehicle down on the ice, so a reduced braking force. And then of course a higher braking force due to static friction slowing the vehicle down on the asphalt side. This is our clockwise torque that we saw earlier. This of course can be mitigated as much as possible if the wheels don't lock, and it's where the ABS comes into play. This system recognizes when a vehicle's speed comes very close to zero or reaches zero, while the vehicle speed is still far from zero. Its response is to rapidly pulse the brakes to allow them to continue rolling This maintains the static one point of contact between the wheel and the road and allows static friction to be regained. Friction force to stop the vehicle will now be increased on the ice side, and any friction force imbalance between the icy surface and the asphalt should be reduced or eliminated completely, thus returning the vehicle to a state of stabilization. Additionally, the added benefit of ABS is that it allows the driver to continue steering the wheel if the wheels are not locked. Inertia is part of the cause for a vehicle having a force imbalance and a swerve when accelerating, braking, or steering on a slippery road. Inertia is why you feel yourself being pushed back into your seat while accelerating, because the vehicle wants to stay at rest and wants to return to its original position, and also why you feel yourself coming forward into your seatbelt when you brake, because the vehicle wants to continue moving forward. Steering is a change of direction, and this also is met with resistance, the feeling of being pulled sideways out of your seat when you turn, because the vehicle wants to continue moving in its original straight line path. Steering on a slippery surface causes much more danger and instability since there is reduced friction to counteract the force of the moving body's inertia and momentum to resist change of speed or direction. We went over quite a lot of information and relatively in depth in this video, so I'll leave you with a quick summary of everything we discussed. And also leave a few note slides at the end of the video that you can look at on your own time by pausing it. So ESC, the electronic stability control system, stabilizes the vehicle by cutting off power to slipping wheels due to over-acceleration and over-torque. The Antilock Brake System, ABS, stabilizes the vehicle by pulsing the brakes on wheels that have become locked after a forceful braking event to allow the wheel to regain a rolling motion instead of a locked skidding motion. Rolling motion allows for the consistent one point of contact between the wheel and the surface, which is what we want for effective vehicle control and effective stopping. Also, a locked wheel results in sliding of the wheel, which is kinetic friction, and over-acceleration on a surface with low friction results in the wheel slipping and a loss of contact between the wheel and the surface, which is also kinetic friction. Static friction force is always greater than kinetic friction, so we never want a situation where kinetic friction is involved. The ESC sensors identify when a wheel is slipping, excess wheel RPM, relative to engine RPM and vehicle speed, and also relative to the RPM of other wheels that have traction with the ground and are not slipping. The ABS sensors can identify when a wheel RPM is 0 or is about to reach 0 relative to the vehicle speed and also engine RPM. If the wheel speed is much lower than what it should be for a certain vehicle speed as a vehicle is slowing down, the ABS can recognize that that wheel is most likely about to lock. The ESC and ABS systems work together to compare individual wheel speeds to identify abnormalities, and this is how both of these systems can work together to ensure safe driving of your vehicle and to quickly regain control of your vehicle. So hopefully you've gained a newfound understanding and appreciation for some of the safety systems that are built into modern day vehicles and hopefully built into your vehicle as well. And now you can think about these different things if you drive on an icy surface or a snowy surface, or if the road is really wet, or if even one side of the road is wet or icy while the other side is dry. You can now understand and hopefully remember what happens if you brake on a road like this or when you accelerate, and how your vehicle would behave during each maneuver, as well as how your vehicle would also behave if you steer on a slippery surface or where one side of the road is slippery and the other side is not. You can see the different kinds of responses that the vehicle would have in each unique situation. So now you can bring your newfound knowledge of physics with you every time you drive your car and hopefully avoid any kind of dangerous maneuvers. Lastly, I'll leave you with a few note slides that you can look at your own time and pause the video to read them as you want to. Thank you for watching, and if you have any questions or comments, please leave them in the comments below. I'd love to discuss this stuff further. Thank you very much, and consider subscribing if I earned it.